Hello and welcome. We are going to work on section 4.2 today. This is our first day of it, so I'm calling it A. We have 3 days coming at us. As you can see in the calendar, it's 4.2A, B, and C, each taken on a different day. Very important topic. It is all about straight line motion, so either horizontal particle movement or vertical particle movement. We're going to look at position, acceleration, velocity today. Well, position, velocity, acceleration. Better to say it in that order. So let's just get started. One important application of derivatives in calculus is particle motion. The three equations that are most important, it won't do it, so I got to write it, is position, which is typically written as S of t or x of t. Those are the common notations you'll see. Velocity. Velocity is the first derivative from position. So those are common notations. And acceleration. So it's the second derivative from position, or first derivative from velocity, finally lands us at A of t. Another thing to note, speed versus velocity, they are not the same. Speed is the absolute value of velocity, which means speed is always either positive or zero. So much like the speedometer on your car, it talks about the speed that you're traveling. Important to note, in AB, we do what is called rectilinear motion, meaning the motion only happens along a straight path. So either that straight path is going to be horizontal or vertical. Position describes where our particle is at a particular time. So if I can put in the time, I can come out with where it's located, how many feet or miles to the right, to the left, things like that. Velocity is the change of position, so it is a rate of change. We can say, we know this, that v equals s prime. Oh, here we go. If the velocity at a particular time is positive, that means the object is moving to the right if I'm talking horizontal movement. If I'm talking about vertical movement, then a positive velocity obviously would be moving upward, like you would anticipate. If velocity is negative at a certain time, then I know my object is headed to the left. And if an object, if it's up vertical movement, then it's headed down. If my velocity is zero, meaning I have no change of position, the object is stopped, both horizontally and vertically, depending on what type of motion. Speed, just to repeat, speed is absolute value of velocity. Going to drill that in your head. And acceleration is the change of velocity over time, right? Because a derivative reflects on the previous equation that I took the derivative on and creates this rate of change. So acceleration is a derivative off of velocity, so that means it's the change of velocity over time. We know this to be a derivative, and thus we can say that A of t equals v prime, which is equal to s double prime. On your car, you have two devices that can change your velocity. What are they? See if you can think of what those would be. One I can think of is if I step on the gas, I can change my speed, my velocity. And the other thing that can, reduce the velocity is the brake. I can change my velocity with those two. Acceleration, let's talk about positive acceleration versus negative acceleration. So positive, if I put in some t value and my acceleration turns out to be greater than zero, then I know my object is accelerating to the right, or upwards, if that's the movement style. And then if it's negative, then the acceleration is towards the left or downwards. And if acceleration equals zero, that just means there's no change in velocity. So it would just be, the velocity would be staying constant. Just because an object's acceleration is zero does not mean that the object is stopped. It just means the velocity isn't changed. The only time we get an object stopped is when velocity equals zero. or the change of position equals 0. What device on your car keeps the acceleration, what's the rest of the words there, keeps the acceleration equal to 0? How do you get a nice steady velocity? You set the cruise control. Also, just because you have a positive acceleration doesn't mean that you're moving to the right. For instance, suppose you are walking to the right when all of a sudden a large gust of wind started blowing to the left, or in other words, we have negative acceleration. What would occur? I would slow down, wouldn't I? My velocity would slow down. So what I want to do is look at this interaction then between velocity and acceleration, because often you're asked, is the object speeding up or slowing down, or is it staying constant? And in order to know if it's speeding up or slowing down, we have to know two things about it. We have to know its velocity as well as the acceleration, the force acting on velocity. So if my velocity is positive and I come in with an acceleration that's positive, so I'm walking this direction and the wind comes behind me and pushes, obviously we're going to speed up, right? If velocity is positive but acceleration is moving to the left, then I'm going to slow down. So I noticed that velocity was positive and acceleration was negative. When they have different signs, it's always going to slow down. If acceleration is equal to 0, it just means I have no force acting on my velocity. So velocity stays constant. I'm going to write that as a constant speed because that's what the directions said. Yeah, we'll just maintain. It's like setting the cruise control. If velocity is 0, but acceleration's positive, then it's going to slow down. One of each sign, a positive and a negative, kind of create negative. Think about that. Like if I multiplied those two, I would get a negative. It slows down. If I have negative velocity and negative acceleration, negative times negative makes this speed up. It creates a positive, so it's going to speed up. Think about it this way. My velocity was negative, so I was walking to the left, and acceleration was a force to the left, then it's going to speed it up. You're acting in the same direction. If A of t is equal to 0, then no effect on velocity. The constant, it just maintains a constant speed. Your cruise control set. If velocity equals 0, and acceleration is positive, well, if velocity equals 0, that means our object is stopped, doesn't it? And same thing here. Anytime velocity equals 0, we have no change of position. And if acceleration is 0, it's still going to be stopped because velocity is 0. So hopefully that little chart will help you. To determine intervals where particles are slowing down and speeding up, we generate usually a sign chart. And that's going to be something new that I'll introduce you to today for velocity. And we can also introduce an acceleration sign chart and a third chart that we can call motion, which is the product of those first two. Like I said, if I had a positive velocity times a positive acceleration, I'm going to get a positive result, meaning it's going to speed up. And if I have a negative one and then a positive of the other, then they multiply to give me a negative. Things are going to slow down. Okay, displacement. There's just tons of definitions today. Displacement is the net change in position. So how much change from where I began to where I finished, right? Usually I do finish minus beginning, and that gives me my displacement. Average, and that's what I'm indicating here. Ending time, beginning time. So position at the end minus position at the beginning. Average velocity, we have done this. This is what we refer to as AROC, the average rate of change. S of t sub 2 minus S of t sub 1. Position at the end minus position at the beginning over time 2 minus time 1. So this really gives us change of position over change of time is what that's really calculating out, and you can see how that is a slope. Questions involving motion are common on the AP exam. We will be able to use, if I can finish the sentence here, where do I got it? We'll be able to use these equations and take derivatives as needed to answer questions involving motion. To answer questions on particle motion, we must be able to decode the questions into math equations. So consider the following. I don't know where my phone is, but I hear it whistling. Let's convert this stuff. So the bug is stopped. What would I look at to know if a bug has stopped? Well, I'd look to see if v of t equals 0, right? Velocity equals 0. Steps to solve. If I wanted to find out when that bug is stopped, I would take v of t, set it equal to 0, and solve for t, right? And then that would tell me the time at which the bug is actually stopped. The bug is moving to the right. Well, that is based on velocity. So I need to know v of t when it's greater than 0. So I would take and set v of t equal to 0 and then use a sign chart. What do I write? Use sign chart. I'd find the t values that make it 0, and then use sign chart so that I can figure out when the velocity was positive and when it was negative. You'll understand more once we get going. The bug is moving to the left. Well, then I need to know when this velocity was less than 0 or when it's velocity negative. Once again, just like the previous one, I want to set v of t equal to 0. And then I'm going to make a sign chart or use a sign chart. What a sign chart does is it allows me to fill in intervals whether the velocity was positive or negative, and that'll be very helpful in determining whether it's moving right or left. When does the bug turn around? Well, in order for a bug to turn around, I have to have v of t changing direction. V of t changes direction. Or it changes signs. Changes from a positive to a negative or negative to a positive on the velocity. Once again, what am I going to do? I would just say set v of t equal to 0 and use a sign chart. These sign charts must be a big deal, huh? They are. The bug is speeding up. In order to know speeding up, I need to know velocity and acceleration. V of t and a of t, so velocity and acceleration, have the same signs. Either they're both positive or they're both negative. So I would check v of t and a of t for their signs. And that might be through a sign chart. Okay. The bug is slowing down. Well, this means then, if they're speeded up, if they were speeding up and had the same signs, well, then they must have opposite signs on this one, right? V of t and a of t have opposite signs. One will be positive and one will be negative. So in order to figure that out, just like last time, we're going to check what v of that time frame and a of that same time give us for their signs. And then I can make the determination. Okay? I have no idea where that's at, you guys. Okay. Finally, we get to some examples. Woohoo! Example 1. For example 1, time is on the interval from 0 to 8, so that's all I have to worry about. The position of the bug moving along the x-axis is defined by this cubic. And what is the position of the bug when it first starts walking? What is the position of the bug? Well, position then indicates, and they used an x of t, position is the x of t function, right? And I want to know when it first starts walking, so let's look at time 0. Where is it in the beginning? And 0 is our initial time, isn't it? So I'm going to look at x evaluated at 0 ends up equaling 0. Trying to make this more user-friendly for you. 1/3 of 0 cubed minus 7/2 of 0 squared plus 12 times 0 plus 2. So I get x of 0 is 2. Doesn't give us any units, does it, on this one? So 2 units, I don't know what those would be, centimeters, inches, whatever, but some sort of length. At what time is the bug stopped? Well, when does the bug stop? The bug is stopped when the velocity equals 0. So now, instead of putting in 0 for time, I'm going to set my function equal to 0. So I'm going to take x of t and set it equal to 0. So we will have 1/3 t cubed minus 7/2 t squared plus 12t plus 2 equals, oh, dang it, I goofed that up. I don't want to know when its position is 0. That's position function. When it stopped, did I point at the wrong thing? I want velocity. I want velocity equals 0. Just realized that. Okay, scratch that, erase. Hopefully you always take notes in pencil. I would. All right, so I need to get to velocity. I need v of t equals 0. To get to v of t, I need to take the derivative of the position function. So this is going to look like what 3 comes down. We're going to have a t squared minus 7t plus 12 equals 0. There we go. Way more manageable. T minus 4, t minus 3, right? One way to find solutions to an equation or find its zeros is to factor. Looks like we get t equals 4, t equals 3. Check to make sure they're on our interval. They are. So when is it stopped? At t equals 3 and t equals 4 would be our answer. On what intervals is the bug walking to the left? To the left means that I want to look for velocity. Well, let's go back and see what that chart said. Moving to the left, I want to look for the velocity being less than 0. Look for v of t being less than 0. And I have my v of t up there, so I want t squared minus 7t plus 12 being less than 0. I'm going to set my velocity equal to 0. I'm going to find my 2 time frames, and I'm going to create a sign chart, okay? So these are what we call critical points. We will get into more of that probably in Unit 5, but they're my ones that I'm really interested in. It's when the position, the particle is stopped, and things could change, right? They could change direction because you kind of got to stop to turn directions. So this is what a sign chart will look like. I'm going to do it in blue. So I just make like a number line, an axis. And on this one, since we're on the interval 0 to 8, maybe I might even just cut the ends here and make hard ends on my number line. That's supposed to be an 8. And then I'm going to pop in my 2 spots. And obviously, I'm not making this super to scale. but I do want some space so that I can work with it. Now, in order to know a sign chart, 3 and 4 are the only spots that break this into intervals where the sign actually does change. So that's a key. So I want to check something in this interval. I'm going to check a number in this interval, and I'm going to check a number in that last third interval. Maybe my number here, I'll check 1's easy, so I'm going to use 1. Maybe I'll use 3.5 here. And on this one, I think I'll use 5. Because any number in those particular intervals will create the same sign. So up above here, this is going to report the velocity sign. And when I put 1 into the velocity equation, I'm going to do it off here to the side so you can see what I'm doing. I would end up with, I want this in the factored form, t minus 3, t minus 4 equals 0. If I put 1 in, I would have 1 minus 3 and 1 minus 4. And from that, I can see I've got a negative value times a negative value, which gives me positive. So this takes on positive velocity. If it's positive velocity, let's see, I wanted to go back here. Too slow. Positive velocity means I'm moving to the right. Okay, so down below, these sign charts hold so much information. Down below, I am moving right. So this would be like my x of t, the position is moving to the right. Between 3 and 4, if I put 3.5 in, let's go v of 3.5. That would give me 3.5 minus 3, 3.5 minus 4. Easy to tell that this would be a positive result. I don't really need to know the numeric value. I just need to know the sign, and that's why these are called sign charts. A positive times a negative gives me a negative. So this turns out negative, which means my particle is moving left. And between 4 and 8, let's use 5. V of 5 equals 5 minus 3, 5 minus 4. Positive result there, and a positive in the other parenthesis yields a positive. So this comes out positive, and now I know my particle is moving to the right when it's between time 4 and time 8 seconds, minutes, hours, who knows? Didn't tell us. So when is it moving to the left? Well, the only interval that I can see that it's moving to the left is between 3 and 4. Where are we going to put that down at? Moving left on time between 3 and 4. Okay? Kind of fun to do. Sign charts are not hard. It is a lot of analysis like this. I wrote it out this time. You probably will get where you don't have to actually do all the writing out because you can keep track of positives and negatives and keep multiplying them out. Example number 2. We got 3 examples to do today, so I'm going to try to keep moving along so this doesn't get super lengthy. The position, the x-coordinate of a particle moving on the x-axis is modeled by the function x of t equals blah, 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 for t greater than 0, where x is measured in centimeters. Okay, we got a units this time, and t is measured in minutes. We have our function, that's important, obviously. And we have a time frame. This time goes from 0 all the way out, right? Find the displacement of the particle during the first 2 minutes. Well, displacement, look back. Wasn't on the first page, but it was on the second page down here. And it says displacement is the net change in position. So displacement, change of position. So what I want to do is look at, and this one was in the first 2 minutes. I'm going to examine where it was at 2, so x of 2 minus x of 0. because the first 2 minutes, so that would say time equals 2, okay? And to do that, now I'm going to plug in my values. So I'm going to end up with 8 minus 2 squared is 4. 4 times 4 is 16, plus 3. Take away, throw in our 0, and we get 3. And this change of position, I'm getting negative 8 in my head, but I want to make sure I don't make a mistake. Negative 8 centimeters is the change in position, which is displacement. Very good. Part 2, I was just seeing if I wanted to erase my previous stuff, but I don't think I want to. We move these down. It says find the average velocity of the particle during the first 2 minutes. Oh, average velocity. I remember I'm seeing something about that. Not the front side of notes, but the back side of that first page. Average velocity, right? Use your notes. So, average velocity, AROC, first 2 minutes. So that's important too, that we notice the time frame. So this would be t equals 2 because of the 2 minutes. So I'm going to start at t equals 0 to t equals 2. I want to look at x of 2 minus x of 0 over 2 minus 0. What we're calculating here is the change of position over the change of time. X of 2, well, we did x of 2 minus x of 0. We already calculated that in step 1. So that was negative 8 centimeters. And then 2 minus 0 is 2. That is a time element. Our time was minutes. So I'm going to get negative 4 centimeters per minute. Perfect. Let me look at question 3. Don't think I need previous information. So I'm going to clear my screen here and get some more information. While I'm doing that, why don't you read the next question? See if you can start setting it up. I don't know, this is really frustrating when you try to erase. Because the normal circling technique doesn't seem to work real well. Nope. All right. The next question, number 3. Have we got it started? All right, there we got it. Number 3, find the velocity of the particle. Oh, velocity. Velocity is a first derivative, right? You can look on the very front side. Velocity equals x prime. So let's do an x prime. I am going to take x prime of t, which gives me velocity. And I like to write that relationship. I would do it on the AP test because it shows knowledge of where you're getting v of t. I'm going to get 3t squared minus 8t. Examine it at time 4. So x prime of 4 is v of 4, which is 3 times 16, 48 minus 32 gets me 16. And velocity is a rate of a change of position. So it's going to be centimeters per minute. It's a rate. Number 4. Find the acceleration. Oh, they have this in such a nice order because it's just leading us from one derivative down to the next. Acceleration, based on the front page, you know that acceleration is equal to the second derivative. So I'm going to say a of t is equal to v prime. How about that? I need to take one derivative from velocity and I can get to acceleration. So I'm looking back here where the velocity was defined. I'm going to get 6t minus 8 They want to know acceleration at 4, so I need an a of 4. Gets me a 24 minus 8, so 16 again. Now, the previous units for velocity was centimeters per minute, and acceleration is a change in velocity, so it's a change of minutes per minute then. You can write this as 16 centimeters per minute squared if you wish. Okay. And finally, the last question, question 5. Oh, is the particle speeding up or slowing down at t equal 4? Oh, I forget how to tell that. What will I be able to do? Well, I could go to the bug analogy, and I know there's some speeding up, slowing down there. It says they have the same side if they're speeding up, and they have different, oh, I shouldn't say they. Velocity and acceleration have the same sign, means they're speeding up. Velocity and acceleration have different signs, slowing down. It also is indicated in this chart here. So, is the particle speeding up or slowing down? Well, they kind of kindly walked us through these steps. So I need to compare. Let's write down what we're doing. We're going to compare, let's put velocity first. Velocity at 4 and acceleration at 4. And I know v of 4 was equal to 16. And I know that a of 4 was also equal to 16. More important, v of 4 was greater than 0, and a of 4 was greater than 0. Since they both are positive, the particle is speeding up. So we got to justify. And justification in calculus is a strong sentence. You really do have to describe what's happening, when it's happening, with your evidence. So I'm going to say since v of 4 and a of 4 have the same signs, because that's all it takes for it to work, have the same signs. I don't even have to describe that they're positive. The particle, don't say it's, because we never know what it's is. The particle is speeding up, and that will not get you full points, because when is it speeding up? It's not always speeding up, I can guarantee you. It's speeding up at t equals 4, I think it was minutes, wasn't it? Yeah, minutes. So even though I described a of 4 and b of 4, I still want to display my knowledge that things are happening at 4 minutes. Okay, so that would be a nice, perfect answer for justifying. The last thing is interpreting the motion from a graph. Whew, getting tired. When is the particle moving to the right? Ooh, good question. So the figure shows the velocity v equals x of t of the particle. I'm wondering if that shouldn't say, let's put a prime in there. That just seems to be a typo to me. Velocity equals x of t. Yeah, definitely. When is the particle moving right? Well, it moves right when v of t is greater than 0. You have to, there's all kinds of places where you can look to see when is a particle moving right. I know that it moves right when the velocity is positive. Now, what I need to do is go over to my graph and look, where is velocity positive? Well, it's positive when it sits above the x-axis, right? So any time frame where my curve is above the x-axis is when it is moving to the right. So, let me get back to a pen here. We would have from 0 to 1. 0 is included in, so I would say 0 to 1, and, oh, what is that point there? That's a hard point to get. That point is 4 2/3. And it looks like it finishes at 7, which I'm going to put a hard endpoint on as well. Now, how did I come up with 4 2/3? I have to use the slope of the line to figure this one out. So what I would probably do is write an equation about this particular line so that I can set it equals 0 and find out when it crossed the x-axis. So to find 4 2/3, here's what you would do. I got to get off that calligraphy pen. That works terrible. Here's what you would do. You would take and know that I've got 2 points. I have 2, -2. I have 6, 1. And normally for the AP, they would actually put those so you wouldn't have to guess at those either. But I would find the slope of that line. Can I do it without? So I went up 1, 1, 2, 3 over 1, 2, 3, 4. So it's got a slope of up 3 over 4. And then I can use y minus, I'm going to use the 0.61 and 3/4 x minus 6. And that's going to give me y equals 3/4 x and 3/4 minus 18/4. 18/4 is 9/2. And then I'm going to add that 1 over, which gives me y equals 3/4 to -7/2. Whoops, x in there. Now, I want to know when this equals 0, so 0 equals 3/4 x minus 7/2. It's kind of a process, isn't it? And 7/2 equals 3/4 x, multiply by 4/3, and I get 28 over 6, which reduces to what? 14 over 3, which gives me 4 2/3. That's how you get that, okay? Not unexpected that the AP would require that of you, okay? It's algebra, it's algebra, it's algebra, and you should be able to do algebra. All right, when is the particle moving to the left? Well, that's a nice question. I like that question. Moving to the left when velocity is 0, which is when it's below the x-axis. So let's go name those. That it looks like it's just one interval, doesn't it? One interval, and that would be when v of t is less than 0, and that would fall on the inner interval. So I'm going to use open brackets, 1 to our special number 4 2/3. The justification is going to be when the velocity is less than 0. So I'm not writing out full sentences here. I know I should, but I want to keep this a little bit shorter. One is the particle's acceleration, positive, negative, and 0. So acceleration is v prime, isn't it? It's the derivative of velocity. Or it's the slope of velocity. So when the slope is positive, or when velocity is increasing, a of t is greater than 0. When velocity is decreasing, or the slope is negative, a of t is less than 0. So from that, I'm going to go up to my chart, and I can see that this is velocity decreasing. So from 0 to 2, velocity is decreasing, which means A of t is less than 0. And is there another spot where we're decreasing? Let's look. Yeah, right here. So from 6 to 7. When is it increasing? When we're moving this way. So on the interval from 2 to 6, and since they're interiors, I'm going to use open ones. And when is the acceleration 0? Well, I don't have any place where velocity is unchanged. So when velocity is constant, like it stayed always at 2 or 3, we would see a horizontal line on our graph. When velocity is constant, A of t equals 0, and this doesn't happen. No intervals, or no time frame, or something like that. No intervals. Okay. When does the particle have the greatest speed? All right, speed. What was the definition of speed? Ooh, I remember that was in our notes. Where was it? Speed, right up here in the block. Speed, absolute value of velocity. So I'm going to either look for the highest value in velocity graph or the least value on the velocity graph. So highest value or the least value of velocity. So I go to my graph. Looks like we have a high of 2, right? And we have a low of -2. Looks like it happens twice, doesn't it? It says when. So when velocity at 0 equals absolute value of 2, which gives me 2. And also I noticed the velocity, what number was that? Velocity at 2 here. So 0 gave me that one. When time is equal to 2, I get out a velocity of -2, but absolute value of that, and I get 2. So when does it have greatest speed? Occurs at t equals 0 and t equals 2. What was our units? Minutes? Was there anything? Nothing given. Okay, so we don't have to label then. Finally, the last one is the tricky one. Oh, there's actually 6, isn't there? Ugh. When is the particle speeding up? V of t is greater than 0 and V of t is increasing. Because that means then that A of t is greater than 0. Remember, we have to have same signs. Do we have the scenario where V of t is greater than 0 and it's an increasing slope? So greater than 0, I'm looking at this yellow region, right? Because that's where velocity is positive when it's above the x-axis, and it's increasing. The only place I see that happening is between 4 2/3 and 6. Trying to decide how I'm going to write that. 4 2/3 and 6. V of t is less than 0, so this is going to be that below the x-axis region, and I need the signs to be the same, so I need, since velocity is negative, I need A of t to be negative, which means that the slope of velocity is negative. So that we can write as v of t is decreasing. So when does that happen? We're looking in the blue region, right? I'm looking down here in the blue region. And I need velocity to be decreasing as well. So velocity is negative because it's below, and then the slope of velocity is negative, and that is 1 to 2. I think that's one of the harder questions, is this one right here. Okay. When is the particle slowing down? It's going to be on the other time frames. It's going to be when v of t is greater than 0 and v of t is decreasing, which indicates to me that a of t is less than 0. And then v of t is less than 0 and v of t is increasing. So the slope is positive, which means a of t is greater than 0. And when does that happen? So we want v of t positive. That's going to be in the yellow zone, and we're looking for negative slope. It's decreasing. That is going to happen right here at 0 to 2 and 6 to 7. Oh, maybe it was 0 to 1. I got to look at that again. 0 to 1, sorry. 0 to 1, and I think it was 6 to 7. I'm going to look at my sheet. Yep. And then 6 to 7. You know what? On these, hard bracket or soft bracket, these are always kind of tricky. The AP takes either, so I'm just going to leave them. I think they probably really should have been hard. And then the last one, I want to be below the x-axis, and I want the slope to be positive. Below the x-axis, so that's the blue, and the slope being positive is going to land me between 2 and 4 2/3. 2 and 4 2/3. 2 and 4 2/3. Good thing we figured out that number a long time ago. I'm going to put hard brackets. You can change these to hard too if you want. Alrighty, that is a long lesson. I wanted to cover enough of it so that you get the idea of it, give you enough examples. So your homework is to work on the motion worksheet. That should follow very closely to what we just did. Have a good day.